to talk today about the second law of thermodynamics. And the second law of thermodynamics says that if you have a closed system, entropy is either going to increase or it's going to stay the same. And if you have no idea what this sentence means, that's totally fair, because it includes a lot of words you probably haven't heard in those contexts before. So the first one to understand is going to be closed system. And what a closed system is just a system that you're not doing anything to. So if you're leaving it alone, you're not adding any energy, it's not getting energy from the sun, it's not being heated up or cooled down, or really having anything happen to it from the outside. It's a closed system. And entropy is a fancy physics way of saying disorganization. So what we're really saying is if you don't do anything to a system, it's going to tend to get more disorganized or stay at the same level of organization. And on a microscopic level, if you're talking about like temperatures, this is pretty hard to understand. But on a macroscopic level, it's totally normal. So macroscopic here is like the real world, the world that we have a lot of experience with, where we can understand things intuitively. So you can see it really easily in like a cucumber. So a cucumber is a highly organized vegetable, right? It's got its cylinder shape, it's got, skin on the outside, it's got a little set of seeds on the inside and a little star pattern going straight up. It's got cucumber flesh, it's, an organized thing. It's clearly a certain shape that is important. But if you take your cucumber and you leave it in the fridge for a couple of months, you're going to get a pile of glop instead, because all of the little bacteria and fungal spores and everything on the outside of the cucumber when you put it in the fridge are going to start decomposing it, and you'll end up with glop, right? And the glop is not organized. It hasn't got a definite shape. It's just kind of a puddle. It hasn't got, any internal structure. It isn't like, oh, I've got fungus glop over here and bacteria glop over here. It's kind of just, a mixture of all the random decomposition products of a cucumber. So it's much, much less organized. So this is an example of entropy increasing because the disorganization of the glop is much greater than the disorganization of the cucumber, which is pretty organized. Now, if you were to take the glop and you were to put it in the fridge for another couple of months, you'd still end up with a pile of glop, right? It's not going to reassemble itself into a cucumber again. That would be entropy decreasing, right? Because your organization would increase. You'd have a cucumber again, which is a complicated physical system, instead of your pile of glop, which is very simple and not organized. So there, your entropy has stayed the same. And this exact same thing happens on a microscopic level, not with glop, but the disorganization increasing or staying the same, it happens between molecules and atoms too. So if you want to understand this in the context we normally talk about it in thermodynamics, you need to think about what temperature means to a physicist rather than what temperature means to like a chef or a weatherman or something, right? When we talk about temperature in physics, what we're actually talking about is how fast the molecules that make up an object are moving. So in a hot object, molecules are going to be moving really, really fast. And in a cold object, they're going to be moving pretty slow. They're just not bouncing around as much. And we interpret these two things on a macroscopic scale as being hot and cold. So if you were to take a hot copper block and a cold copper block, leave them in a box, walk away so that the system is closed and you're not doing anything, they would tend to end up the same temperature. You wouldn't have a hot one and a cold one anymore. And this is because your initial system has a fair amount of organization to it, right? On this side, where the atoms are moving really fast, it's all hot. On this side, where they're slow, it's all cold. But you put them together so that atoms can move between the two. And in like the real world, if these were people, you wouldn't just have the fast ones over here and the slow ones over here. The fast ones would start running into the slow ones, and they'd end up as a mix of speeds. And it would, equilibrate. It would all become the same. And so this is the exact same thing happening, just on a smaller scale. And, reinterpreted up to the larger scale in the terms we understand things on the large scale. And that's how the second law of thermodynamics works in a physical system. Bye. I've been Eliza McDonald. It's been nice to talk to you.